guys, so what we're going to do is we're going to do the calculator work part of this. So you're going to need to know your expected chart, and we're also going to need to know our original observed value. Okay? So I'm just going to put this over here so I can get to them in a second. So then what we're going to do is we are going to finish up our birthday problem. We're going to do it on the calculator. Really appreciate it if you've done it by hand yet. If you haven't, then this will just be like, oh yay, matrix. Yeah, so we do get two matrices. So what we're going to do is, if you've never done a matrix before, you're going to hit second and then the x to the -1 power and move over to edit. So we're going to go second matrix. I've already put some stuff in there. So we need to go with row and column. Okay, so we've got 7 rows and 2 columns. Okay, so that's what it looks like. So matrix A is going to be my observed value, what we actually collected. All right, so that looks good. So I'm just going to come into here. I'm going to type in my data. Okay, so that one's done. So then I'm going to go back to second matrix. I'm going to go to edit. I'm going to go down to part B, and I need to change that to a 7. And then I'm going to pull out my my expected counts. Excuse me, my expected counts. So 10.78, 10.22, 11.81, 11.19, 12.83, 12.17, 11.29, 10.71, 12.32, 11.68, 9.24, 8.76, 8.73, 8.27. All right, so then there is my data set into it. All right, so I'm going to write this down real quick so that we have it. So matrix A is my observed, and then matrix B is my expected counts. All right, so then what I'm going to do is I'm going to go to stat, I'm going to go to my tests, and I'm going to go to not my goodness of fit, but my chi-square test. Okay, so then I'm going to hit enter. My observed is in A, my expected is in B. It's all good. All right, move down here to calculate, and so it gives us our chi-square, which is 6.55, and then we get our p-value of 0.3646, and then we're going to put down our degrees of freedom is equal to 6. So we did our chi-square test, and it gave me that. All right, so that one makes our lives a lot easier if you hadn't noticed. Okay, so that's how you do it on the calculator. Really quick, short, and easy, and then we'll go from there. All right. Hey guys, move this up real quick, or not too quick. So we're looking at the chi test for homogeneity. I hate that word. We want to use the test whenever we are analyzing the results of a comparative experiment with the chi-square test. So the key phrases that we're looking for is several populations or treatments. Okay, everything's the same. Conditions, expected accounts, all of it. How we found it, it's all going to be exactly the same. All right. So what we're going to be looking at is we're just going to be jumping right into an example, and I'll show you that key phrase. Now, when we write out the narrative and everything like that, we need to say we're doing a chi-test square for homogeneity. Homogeneity. Anyway, the problem is called color and candy. All right. We're going to start off with a statistics student decided to investigate other ways to influence a person's behavior. Using 60 volunteers, she randomly assigned 20 volunteers to get the red survey and 20 volunteers to get the blue survey. And then the 20 remaining volunteers would get the control survey. The first 3 questions on each survey were the same, but the 4th and 5th questions were different. For example, the 4th question on the red survey was, when you think of the color red, what do you think about? And on the blue survey, the question replaced red with blue. On the control survey, the questions were not about color. As a reward, the student let each volunteer choose a chocolate candy and a red wrapper or a blue wrapper. And the student would keep track of what candy they selected and the survey they took. So there's our multiple survey, multiple or several populations and treatments. All right. So what we're going to do is we're going to compare the distributions of color choice for each of the 3 treatments. So we're going to draw a bar graph, and then part B says, do these data provide convincing evidence at the significance level of 0.05 that the true distributions of color choices are different for the 3 types of surveys? All right, so the first thing that we need to do is I need to calculate how many in the red survey chose the blue and red, okay? And so what I'm going to do is I'm going to go with, so this is going to be 13 divided by 20, okay? And I already did the work, and that's 65%, okay? And then here, it's 35%. On the blue survey, they chose red 25% of the time, and they chose blue 75% of the time. And then on the control, they chose 40% of the time, and they chose blue 60% of the time. Okay? So then what I'm going to do is red survey. I'm going to do the red first, so that's 65. So if I just draw a quick little like that, and then I can come down here and say 65%. And then the blue is going to match up here. Okay. Now since I did the red first on this survey, I need to do the red on the base as well, so we can have that comparative color. All right. So the red is only about 25%, and then the blue covers the rest of it like that. The control, the red was 40. About screwed up. And then the blue is 60. So then I would come into here and say our bar graph shows the red survey picked more red, and then the blue survey picked more blue, and then the control picked more blue. Okay, so oops, scoot that up for you. So I'm not trying to add anything to it. I'm not trying to make it fluffy. Remember, I'm just stating what I see in my bar graph. Okay. All right. So I'm going to stop it there. We will finish this problem up in the next video, and we'll just keep going from there. Okay.